So okay, in this topic of electromagnetism, what we're going to talk about is what happens when you have a current carrying conductor, or let's say a moving charge in a magnetic field. They will experience a force. So this is called electromagnetism. So that means when there's a current or there's movement of charge, there's a force. So it's called electromagnetism. So there are actually three cases we're going to learn in this chapter. One is the force acting on a parallel current carrying conductor in a magnetic field. The other two, we're going to learn about it later. The second one will be the force between two parallel current carrying conductors. The third one will be force on a moving charge in a magnetic field. So the first one, force on the current carrying conductor or wire in a magnetic field. That means you have this wire, and you see it's connected to this battery here. So the current will flow through the wire, and remember we said from the previous chapter that whenever a current passes through a wire, the wire becomes a magnet. That means it generates a magnetic field. So because it generates a magnetic field, so it is like a magnet, and so if you place it in another magnetic field, so this magnetic field is generated by these two magnets. Can you see here? So if I draw like this, you will be able to see clearly. So there's a uniform magnetic field due to these two magnets. So a magnet, which is a wire in a magnetic field, will surely experience a force. So that is the electromagnetism we're talking about. So force on the wire. So how do we explain why there's a force on the wire? Is because of the interaction of the magnetic field. So we look at the next slide. So if you see the pattern of the magnetic field of these permanent magnets is this way. And then your wire, which you put inside here, has also its own magnetic field. So when you place it inside, they will interact. So at the top here, the magnetic field is in the same direction, so they reinforce and become stronger, which is why you draw the lines here closer. But at the bottom, the magnetic field of the wire will turn downwards, but the magnetic field of the magnet is to the left. So what will happen is, they will cancel out each other. So therefore, we draw them very far apart, means it's very weak. So the top part is a stronger field, the bottom part is a weaker field, so it will push down. So that's the reason, but we don't use this reason to explain an exam. They want you to explain using Fleming's left-hand rule. So how do we use Fleming's left-hand rule? So you can use your Fleming's left-hand rule, so you hold it like a gun. So when you hold it like a gun, you can say what? It looks like saying FBI, right? Like FBI holding a gun. So therefore, this magnetic field, so this magnetic field is represented by this direction. So in other words, there are two magnetic fields here. So which magnetic field do we use? Now always remember, the force on the wire is because there's an interaction between the field of your wire and the field of the magnet. So the field of the wire is actually represented by the current here. So therefore, this other field must be the field of the permanent magnet, because if both represent the field of the current, so nothing will represent the external field. So this will represent the field that the current is in. So in your case, you take this finger and point to the left. So when you take this finger and point to your left, and this current is out of the plane of paper, so the middle finger you point towards yourself, and then you notice the force will be downwards. So that's how you use Fleming's left-hand rule. So we can use this Fleming's left-hand rule to predict the direction of the force. And if we want to measure the magnitude of the force, how do we measure it? So when you have a force on the wire, the top end balance will actually show you a reading. So why will it show you a reading? Because you must understand how this is set up. The wire here is clamped using two retort stands. So it is not resting on this frame. It is actually hanging or suspended between the two magnets. But the two magnets which are attached to the metal frame, it will be heavy. So if you put in a top end balance, it will surely give you a reading, right? So one of the easiest way you can do it is to zero it after you have put on the magnets and the frame. So you zero it, then only you turn on the current. So don't turn on the current, just put on the magnet, zero it, then you turn on the current. When you turn on the current, as the current starts to flow in the wire will experience a force. And if the wire experiences a force, this top end balance will show you a reading. Now let me explain to you why. Now, since the wire is not touching the magnets, so why is it when there's a force on the wire, why does your top end balance show you a reading? because of Newton's third law. Now let's assume the force on the wire can be either up or down. So let's say it's upwards. If the force on the wire is upwards, that means who is exerting a force on the wire? The two magnets, right now. So the two magnets is pushing the wire up. So according to Newton's third law, the wire must push the magnets downwards. So when the wire push the magnet downwards, the magnets get heavier, so you see a positive reading. So positive reading means force on the wire is up. That's why many people confused when they thought positive reading means it's a force downwards, so they thought the wire is moving up. Actually, this top end balance shows you the force on the magnet, which is opposite to the wire. So if the reading is higher, that means it's heavier, that means the force on the magnet is down, that means force on the wire is up. But if the force on the wire is down, then the force on the magnet will be up. Then this will be negative. This will show you a lighter reading. So once you have the top end balance reading here, you can actually convert to kg, because the top end balance reading is gram. You convert to kg, then you times 9.81, that gives you the force. So you can actually measure the force. But let's look at the formula. So from the experiment, you will notice that the strength of the force exerted on the wire here is actually directly proportional to the flux density of the permanent magnets. Also directly proportional to the current in your wire, because the stronger the current, the stronger the field. So therefore it makes sense lah. And also L. L refers to the length of the wire in the field. So not the entire wire. So you have to find out how much of the wire is in the magnetic field only. So you get F equals to BIL. So from here, you can rearrange and get B equals to F over IL. And it is from this equation that we use to define magnetic flux density or magnetic field strength. So what's the definition of magnetic flux density or magnetic field strength? From here. So you will see the definition of flux density is defined as the force acting per unit current in a wire of unit length, because it's F over IL, which is perpendicular to the field. And this formula also gives you a definition of 1 Tesla, because remember the unit for flux density is Tesla. So what is 1 Tesla when everything is 1? So flux density in if a wire of length 1 meter carrying a current of 1 ampere has a force of 1 Newton in a direction at right angles to both the flux and the current. So it's all coming from this single equation. So both you're going to memorize now. So then some people ask me, what happens if the wire is not perpendicular to the field? Because so far our definition, our formulas are always perpendicular. When it's not perpendicular to the field, for example at this angle, then you have to find the component of the current 90 degrees to the field. Or if let's say the wire was straight and the field was at the angle, then you must find the component of field perpendicular to the current. So either one you resolve, doesn't matter, as long as they're perpendicular to each other. So in this case, if I find the component of the current perpendicular to the field, it will be I sine theta, right? So then my formula is BIL sine theta. Now, it means to say when theta is 0, that means theta is 0 means the wire is parallel to the field. Then sine 0 will be 0, so there's no force. So if the wire is parallel to the field, there's no force. But it also means if the wire is perpendicular to the field, then your theta is 90 degrees. So sine 90 is 1, so you get the highest force. So why is it you get highest force when the wire is perpendicular, but 0 force when the wire is parallel? You need to understand, right, regarding the direction of magnetic field of wire. Now remember, to get the magnetic field of the wire, we use a right hand grip rule. So if the wire is vertical like this, if you use a right hand grip rule, that means the current as going up, then the field will be horizontal, circular but horizontal. So if the field of the wire is circular but horizontal, then it will interact with horizontal field. That means it gives you a maximum interaction, to give you maximum force. But if the wire is horizontal, then the magnetic field using the right hand grip rule will be vertical, circular, vertical. So then what will happen is your field is vertical, the external field is horizontal, there will be no interaction. So therefore there's no force. Therefore when the wire is horizontal, there is no force, because the field of the wire will be vertical, which cannot interact with horizontal field. So understand? So now why you have maximum force when the wire is perpendicular. Now to find the electromagnetic force, one of the method is to use the top end balance like just now. But they can also use something called a current balance. So a current balance, how does it work to give you the force? So once again, you will still have your current passing through your wire, and your wire is placed in between the magnetic field. Now we must arrange the polarity of the magnets and also the current so that the force on the wire is downwards. It won't work if the force is upwards. So when the force is downwards, you will notice that because it is like resting on these two pivots, so it's like a seesaw, it can actually start to tilt on either one side. So what will happen is, if the force on the wire is downwards, it will cause it to tilt downwards. So we quickly hang in small weights here until it balances. Okay?
Yeah, but can you just explain the tilting part?
Now because this is like a seesaw, if you apply a force here, wouldn't it start to tilt this way? Like a seesaw? Like you sit a seesaw, you push like that.
Yeah.
So you hang in the other side, then you turn around.
So you put weights to balance.
Yeah.
Okay. And then the amount of the weight you use here will be the
equals
weight
like
equals that, and
There's
then
a
you
force
times
here.
by force.
Yeah.
Okay.
Okay, enough.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.